Question 18. The graphs show possible current, voltage, IV, characteristics for a filament lamp and for a semiconductor diode. So here we have the set of graphs and ask which row in the table best specifies the current IV graphs for the lamp and for the diode. So this is a light bulb that works with this filament right here. So it's called filament lamp. So this is a spring that is kind of supported by those two clips. So when the voltage is applied to those terminals, the current is going to flow through this zigzag here spring, and because it's going to take so many turns, it's going to heat up. This filament is going to get hot, and then it starts to emit a gas. So the gas that is going to provide the light inside this glass here. This filament is going to get hotter with time, not right away. With time is going to get warmer and warmer, and this is going to affect the resistance of this filament. A current voltage graph, if it's linear like this value here will be the gradient of this graph. So the gradient of this graph is the resistance. So in this case, the resistance is constant. An example of the difference between the line of a IV graph, if it is a straight line, let's say that we have two resistors with two different values. So this is 200 and this is 100. So the 200 is higher and the 100, that will be a lower resistance when compared with both, and the graph line will be more steeper when it's lower than when the resistance is higher. You'll be less steeper. Now this filament is going to change its resistance with the temperature. So this is not going to behave like a fixed resistance, like this graph. This is a fixed value, 200 ohms the entire time, with different values for current and voltage. Same thing here, with different values for current and voltage, always going to give the same value, which is 100 ohms. This is not going to happen here. So how we represent the IV characteristics for a filament lamp? When this filament is still at room temperature, it's going to behave just like a fixed resistor with a straight line. As the time goes by, when the temperature of this filament starts to increase, it's getting warmer, so the current is going to decrease. So since the y-axis is the current, so the line is going to get a little bit less steeper as go by, because the current, the value here is not increasing at the same rate that was before, when the filament was still colder. So because the segment line is getting less steeper, like this one, so the resistance is getting higher. So the resistance is increasing. So as you see, the gradient of a IV graph is the resistance, in this case is fixed because the gradient is the same on every single point of this line or this line. But this one is changing, is a curve. So the resistance of a filament is going to change with the temperature. So from this selection, the graph that best represents the filament lamp is P. This is for the filament. Now let's take a look on the diode. This is a diode. A diode is polarized, which means that there is a specific side that needs to be connected to a circuit in order to allow the current passes through. There is a mark here. Is very small, very hard to see, but this is a mark, and that is the negative side, and the other one is the positive. The symbol for a diode is like this. So this side is the negative, and this side is the positive. Besides the polarization, a diode needs at least 0.6 volts on its terminal in order to let the current passes through. So because of the working conditions of a diode, which must be polarized, so positive and negative connected to the right terminals, and a minimal voltage of 0.6 volts. So the graph IV shows that right here there is no current flowing through this diode until the voltage reaches the value of 0.6 volts. Even the voltage before that will not produce any current flowing through this diode. So right here, and what happened is after reaches this minimal voltage value, the current is going to increase really quick right here. So back to our problem, the three options left that can describe the characteristics of a semiconductor diode should be R, because here clearly we can see that up to certain minimal voltage, the current is going to increase really quick. So that will be our R. So for the filament lamp is P, and for semiconductor diode is R. So the option is this one right here. Problem 19. A current contains a cell, two resistors of resistance R1 and R2, and a variable resistor X. The cell has negligible internal resistance. V1 is the potential difference across the resistor of resistance R1. I2 is the current through the resistor of resistance R2, and the resistance of X is reduced. What is the effect on V1 and I2 after this resistance is reduced? Let's take a look on this joint. So here is I1, because that's the current that is flowing through R1 resistor. This is our I2, and this is our IX, the current that is flowing through this variable resistor X. Now the problem states what's gonna happen to I2 when this resistor is reduced. So now this X is low. If X is low value, what is gonna happen to this current? This current here is going to increase. Why? Because current and resistance, they are inversely proportional. just like frequency and period. They are inversely proportional. So if my R is low, my current is high because the voltage remains the same. Remember, so the voltage is RI, is the product of resistance times current. So if the voltage source is constant, so when you increase one value, the other one needs to decrease with the same proportion. So going back to our analysis here, so X is low because the problem states that, and what's going to happen to the current flowing from this X is going to increase. So the resistance decreases, the current increases. So how this is going to affect I2? Well, you need to look now Kirchhoff first law for current. So the current in a joint obey this law. All current they enter, the sum of current they enter in is equal to the sum of currents out. So current that is arriving this knot is I1 and leaves IX plus I2. So I'm looking for I2. What's going on with I2 with this condition? So I2 by this formula is I1 minus IX. So if my IX increases, so what is going to happen? My I2 is going to decrease. I draw another circuit here because we have so much stuff in this one, so a clear one to take a look what happened to the PD or the voltage across the resistor 1 when the X drop its value. Now let's take a look on this circuit right here. So though the X, the resistor X and the resistor R2, they are in parallel, which means that the voltage on both is the same. So if the voltage in this section drop and we have the same EMF here from the battery, from the cell, so if this drop, so this one here is going to increase. So the voltage on this resistor is going to increase because the EMF is the voltage drop V1 plus V, the X parallel with VR2. So this here is going to drop, so this one is going to increase for the same value of EMF. So the voltage on R1 increases. So this problem is kind of analytical type of problem that we don't have numbers to play with. We just need to have an understanding about Kirchhoff first law and how a energy from a battery is distributed between resistors depends on how they are connected. So to answer this question, what is going to happen to I2? I2 is going to decrease. So we have this option and this option. And what is going to happen to V1? V1 is going to increase. So that will be the correct answer, C. Question 20. Two resistors of resistance R1 and R2 are connecting parallel. What is the combined resistance between X and Y? So here is asking basically the total resistance of the circuit. So because they're in parallel, so the inverse of the total resistance is equal to the inverse of the sum of all the resistors in this circuit.